Yep. Hello, everyone. Let's start today's discussion. Before we start, I wanted to ask if there is any question about transfer function and S-domain analysis, or in general, basically, about the course. Any question? Because today we are gonna move on to the time domain analysis, okay, and modeling the system in a time domain using the state space. Okay, so let's start with actually defining the state space. Why is it okay? State space, okay, is a set of n first order differential equations, okay, when we have n variables, okay, to be solved for our modeling and state as a state variables. So when we talk about the state space, we have multiple differential equation, okay, in time. All those variables within that differential equations are going to be linearly independent. That means you cannot define any of those variables as the linear combination of the others. So all of them are linearly independent. Okay. And we are going to solve using algebraic equation, okay, but in a matrix form. The general form of a state space model for any system is the differential of our variables, those independent variables, okay, equal to the participation of all those variables on the differential plus the participation of the inputs on the differential. Does that make sense? This is a vector. This is a vector. This is a vector. So it doesn't mean we have only one variable or one differential in our system, and doesn't necessarily mean we only have one input. So we might have multi-output, multi-input to define and to analyze. Are we good? So we are gonna change our nth order system, which you already know. If we have nth order system, the general equation that describes that system is going to be an nth order differential equation. Are we good? So we are going to describe all those. We are going to basically expand that n order differential equation into n one order differential equation by defining those variables. These variables are not necessarily those x, okay, the vector of x are not necessarily, for example, the parameters that you want to like examine. Okay, they could be the derivative of that parameter or double like the second order derivative of that parameter. We are gonna see as an example, you are gonna kind of like have a better understanding of what I'm talking about. Now, the next equation, this is the first equation is what govern your system, is the model of your system. The second equation is basically your goal of analysis. So for example, you might want to like analyze the voltage across a capacitor. So that's the output of your modeling. This is going to be your y. This is what you want to basically analyze, the parameter, the variable that you want to analyze. And we could describe that specific variable based on the combination of, which, as you know, if we have a matrix, is going to be linear combination of the state variables that we defined earlier, plus the linear combination of whatever input we have in our system. Is that clear? So when we talk about the state space, we have two sets of matrices or differential equations. One is the first one, which models the system. The second one is the output that you wanted to, like, this is your basically desired variable, your output that you wanted to like focus on analyzing. Now, as we said, the x's are the state vectors. We define them is a mathematical representation of the independent variable that we can define to describe our system. I'm emphasizing that they are not necessarily an actual physical variable. This is a mathematical representation that we define. Okay, so we could represent that nth order differential equation governing our system. Okay, we could turn that into the n1 order differential equation. Is that clear? Now, x dot is going to be the derivative of those defined variable in that formula. A is a system matrix. Anyone can tell me why it's a system matrix? You can borrow the concept of the transfer function when we talk about the transfer function. Anyone remember what was the definition of the transfer function? That
S times
yeah,
x's.
we had like a g of s or h of s that describes the output versus input, right? What was the definition of that g, that transfer function? You remember? There was one very specific condition when we defined the transfer function. We said transfer function is a model of our system in S domain, basically defining the output versus input in S domain, assuming what? Very important condition when we want to define a transfer function. Anyone remembers that? We were assumed that the initial conditions are 0. Remember? So that is very important piece of information when we define that transfer function. And we said that transfer function actually represents the behavior of our system. Now, we call this matrix A system matrix. So it represents the behavior of our system. Now look at this formula. If we have 0 initial condition, what that means? That means in time 0, the u is 0. So the whole differential equation depends on matrix A. Make sense? So matrix A is basically the matrix that describes the dynamic of your system when you don't have an input and you don't have any initial condition. Are we good? So B is the matrix, we call it input matrix, is the matrix that defines how the input would participate in the behavior, the dynamic of our system. Okay? Now, when you talk about the output, which is your desired parameter, y is the vector of that desired parameters. You might want to like analyze the current of an inductor and the voltage across the capacitor. Okay, whatever parameters in your system that you focus on as the output of your analysis. This is going to be your y. Now, that output is going to be the result of interaction of whatever state variable that you defined, okay, plus the effect of the inputs. That C defines the participation of those state variables. That D defines, okay, the participation of the inputs in your desired variable, i.e. output. Is that clear? And we know that the U is input, so I can point that. Any questions so far? This is the definition of a state space. So we have an nth order system. We define n variable, okay, n independent, linearly independent variable to change that nth order system to n one order equation. And then we solve for the output that we want. Remember, these x's are not necessarily the physical, this is mathematical representation of the variables. Now, we have to have a minimum number of the state variables. Okay, I have to like fix. I made a wrong statement. If we have nth order variable, we have n order system. We have n minus one independent variable. You are gonna see why. Okay, so sorry for that. So if we wanted to like apply a state space modeling in our system, we need to have the minimum number of the state variable. Okay, and it's basically given if we wanted to like have independently a linearly independent variable is basically we are inherently following this minimum condition. Okay, now as we said, all those state variables or component of the state vector should be linearly independent. And how do we know what is the minimum number? Okay, when you look at your system, the minimum number, okay, is the order of your differential equation, or you can see the circuit or like your physical system is the number of the energy storage component. Now, let's look at an example of nth order differential equation. We have like a 3-order differential equation here. Okay, we said we wanted to like describe that with a minimum number of linearly independent variable. How we do that? We set the order is 3. Okay, okay. Why I did that? The first statement was true. Like the order is gonna be the nth order and independent variable. So we have 3-order equation. So we are gonna have 3 independent variable, which is the minimum number of the variable that we need to describe this in a state space, this equation in a state space. Now, how we define that? We want to have an nth order, an n one order differential equation. So in this case, we are going to have three one order differential equation. Are we good? So what would be the differential equations? We have x1, x2, x3. So we are going to have x dot 1, x dot 2, and x dot 3. Okay? Now, if we define x1 as this variable x, this is this x, correct? And we define x2 as the derivative of x, and x3 as the second order derivative of x. Okay? What would be x1 dot? Is going to be x dot. Now, based on our definition, what is x dot? This is going to be x dot. What is x dot based on our definition? x2. So we have one order differential equation. Very simple. Same goes for the x2 dot. Is going to be x double dot, which is x3. Correct? Now, what is x3? Is going to be x3 dot. Is going to be x3 dot. The third order of our x. Correct? Is a differential of x double dot. Are we good? Now, we don't have that in our definition. How we can find what is the x triple dot? Any idea? We had x1 dot and x2 dot. We could define it based on our definition. How about x3 dot, which is this third order differential of x? We don't have that in our definition. How we could define that? How we could define that as a combination, as a linear combination of our x1, x2, and x3? Any idea?
Repeat the question. Can you repeat the question?
How? See here, when we wanted to like describe x dot 1, we saw that is equal to x2, which we defined. Same for the x2 dot. We defined the x double dot as x3. So based on our definition, we could kind of like develop this second one order equation. Are we good? Now, for x3 dot, it's going to become equal to the third order derivative of the x. We don't have the third order derivative in our definition as a state variable. How we can describe the x3 dot based on x1, x2, and x3? That's the goal, right? We want to define this differential equation based on the state variable. How we can define it? We are going to go back to the original equation. Here, we have x, a third order derivative of x. Okay? And we know that x double dot is going to be x3. X dot is our x2, and x is our x1. See? Now x double dot is a linear combination of our state variable. Make sense? So now this one is gonna be minus 8 x3 minus 6 x2 minus 2 x1. I'm bringing everything to the other side of equation. Plus, now we have our input affecting the differential equation. Is that okay? Are we clear? Now, we said we are gonna represent that in a matrix form. We said we have our vector of x dot, which is x1 dot, x2 dot, and x3 dot. This is that x dot that we talk. Okay, it was x dot equal to ax plus bu. Remember? Okay, now, if we have the x dot as a vector, we wanted to have matrix A times our state variable x1, x2, and x3 plus another matrix times our input vector, which is simply a 1 by 1 vector u, because we have only one input. Is that okay? Are we good? Now, look at, we have three differential equations. So we are going to have 3 by 3 matrix as an A. Now, what is the equation that defines x1 dot? x1 dot is equal to x2, right? So what would be the first row of the A matrix? X dot what is not dependent on x1, so it's 0. It is only had 1 times x2, so this is 1. And it doesn't have x3, so this is 0. Are we good? Same, we can go for x2 dot. It doesn't have any x1 and x2, but it has 1 x3. Now, x3 dot has minus 2x1 minus 6 x2 and minus 8 x3. Are we good? Now, plus x dot 1 do not get affected by u, correct? So 0. Same for x2. But x3 dot, okay, has 2 times u in it. So we have 2 here. Now we turn this nth order, the 3-order differential equation into 3 1-order differential equation. Are we good? And now we can use the algebraic kind of like derivation of a differential equation in matrix form to solve for x dot. Is that good? Are we clear? Now, we said we have another equation that describes the output. Let's say our desired output is, for example, x1. Okay, we want to analyze x1. Okay, so what was the equation? Equation was y is equal to cx plus du. Correct? Now, if y is x1, that means it is x1 equal to what is x1? It's x, right? So it doesn't matter. We have the x1. Now, how we can describe the x1 based on the x's? We have c. We have x1, x2, and x3 plus times u. Since we have our output as equal to x1, so our y, let me describe that by y. Our y is going to be equal to x1. So what is going to be these coefficients of matrix in this equation? the multiplication of x1 is 1. What about x2? 0. Same goes for x3. Do we have u in it? 0. Is that clear? Now, what if we define y as x2 dot plus x3? In that case, what would be x1, x2, x3 plus u? Now, what is x2? X dot 2 is x3, right? So actually y become 2x3. Correct? Are we good? So it's gonna be 0, 0, 2, and we don't have a u in it, so 0. Is that clear? Are we good? x2 dot, we defined it here. We find that x2 dot is equal to x3. Okay? Is that clear? So we represent x2 dot based on a state variable. So this is, if this is equal to x3, y is equal x3 plus x3, which is 2x3. Are we good? Is that clear? Now, let's look at an actual like differential equation that you might see in a circuit. We have C, the second order differential of V plus 1 over R, differential of V plus V over L equal to 0. Now, we have second order differential equation. What that means? That means we are going to have, if this is second order, we are going to have two state variables, x1 and x2. How we could define that? So we have two independent state variable. We define x1 as v and x2 as v dot. Are we good? So now let's see what is going to be our x1 dot and x2 dot. x1 dot is simply v dot. And we know v dot is x2. Correct? This is x. Are we good? Now, what about the x2 dot? Is going to be v double dot. From the equation, we know that v double dot, let's rearrange this. This is v double dot plus 1 over RC, v dot plus v over LC. Okay? Equal to 0. This is L, this is C. So x2 dot is going to be minus 1 over RC times v dot, which is x2. Okay? Minus 1 over LC, v, which is x1. And we don't have any u, so that's it. Are we good? Now, let's represent that x dot equal to ax plus bu. Our x dot vector is going to be the differential of our state variable. Is that okay? We have two state variables, so it's going to be 2 by 2 A matrix times the vector of a state variable, so x1 and x2. Are we good? Plus b u. We don't have u, so we can just ignore this part. Are we good? Now, what is x dot equal to? Is equal to x2. So it's going to be 0, 1. Is that okay? What about x2 dot? x2 dot is minus 1 over LC times x1. So this is going to be minus 1 over LC plus minus 1 over RC times x2. So it's going to be minus 1 over RC. Now we have our state variables. Are we good? Now, here, obviously, we are solving for V, correct? So our Y is V. What is V? X1. So Y is equal to a matrix times, this is, sorry, times x1, x2, and we don't have any u, so I'm kind of like ignoring that du, okay? So this is going to be equal to x1. What is x1? What is y? Is equal to x1. So this is 1, this is 0. Are we good? Is that clear? What we talked about? For a steady space. Any question?
How did you define the dimension of C, of matrix C?
Based on the number of the u that you have
So it'd be
and the number of equations.
So it'd be a 1 by however many.
So
variables.
this B is gonna be an n by m matrix, right?
Yeah.
So you have n row and m columns. Are we good? So how many rows you have in your whole equations? The number of your state variables, right? So n is gonna be the number of state variables. Now you wanted to like define each variable based on the input, right? So the number of the column should be the number of input you have. Is that okay? So if you have two input and 3 state variable, is going to be 3 by 2.
For C?
For B.
Oh, I was asking for C.
C is the number of output that you want. Okay, here so far we only have one output. You might have a vector of output. So you might have the y as a vector of y1 all the way to yn. Correct? Now you have n equation. So C want to describe this n equation based on, let me use another index. Let's say this is k 1 to k. So you have k equation that you want to describe based on n state variable. Okay, so it's gonna have k row and n column, because eventually you want to multiply that by the x vector. Make sense? Are we good? Anyone have any question? No? Let's look at an actual circuit. We already saw that integrator circuit using an op-amp. And before we already run the KVL and we find out that the V out is minus 1 over RC, the integral of V in du, dt, right? Is that okay? So if we run an differential over this to get rid of that integral, we are going to have V out dot equal to minus 1 over RC V in. Correct? Now, how many state variables should we have? How many state variables should we have? One. This is very simple. You know what I'm saying? So you don't need to have multiple state variable always. You have first order differential equation. So your state variable is only one. One state variable. Are we good? So you only have x1, okay, which is gonna be V out. So x dot 1 is gonna be minus 1 over RC V in. What is V in? If you want to describe it based on that AX, this is x dot AX plus BU. What is V in? Yeah, it's our input. Correct? It's not in our system. It's what we injected as an input. So this is gonna be U. Correct? So define this as a matrix. It's not worth it to have a matrix because it's one differential equation. So x1 dot is gonna be some multiplication A times x1 plus another multiplication times U. You have the differential equation here. What is gonna be A? How many x1 you have in this equation? In this equation, this is x, x dot 1 is minus 1 over RCU. 0. So x dot doesn't depend on x1. And how many u you have? Minus 1 over RC. Is that clear how we get there? Now here we only have one variable because we only have one energy storage component in our system. And when we have one energy storage component in our system, the general differential equation is going to be first order. So the state variable, the state space are going to be one variable. Make sense? Like in practice, you don't need to use a state space variable to define, to analyze this because it's a first order. Okay, the whole purpose of a state variable, a state space was to simplify that nth order differential equation into n one order differential equation. Okay, now you have one order, so it doesn't, but I wanted to like get a little bit of perspective of what's going to happen. Are we good? Any question? No? Now, let's again go through how we can develop and a state space model. It goes without saying. First step is to know what system you want to analyze. So you select your system that you want to analyze. Are we good? Now, you run the analysis based on the engineering theories, and you are going to end up in an nth order differential equation that describe your system. Okay? And you are going to turn it to the n simultaneously first order differential equation based on the state variables that you defined. Are we good? Now we are going to solve all those one order differential equation at the same time. Okay? And then the result is going to be the algebraic combination that y we defined. You see, y is c times x plus d times u. What is this c? Is a linear combination of the component in x, right? Are we good? So y is the algebraic or linear combination of the state variables plus the linear combination of the system's input. Are we good? Is that clear? Now, we are going to have some example session that we actually run some numeric kind of like example, and you're going to see how we actually solve those equations in order to get the final answer in our circuit, okay? Or in any type of system. Any questions so far? No? Let's look at an actual example. We have an RLC circuit, a series RLC circuit. We already know that the KVL in this RLC circuit is going to be LdI dt plus Ri plus 1 over C, the integral of the current, and it's going to be equal to the input, to that source. Are we good? We run a derivative over I to get rid of this integral, okay? So we have a second order derivative, and you remember we define the derivative of I as dq. We define dq over dt as the I. Remember, we had this discussion before. So now we have a second order differential equation, okay? And we need two state variable, x1 and x2, correct? Because we have second order. Are we good so far? We consider x1 as the q, and we are going to consider x2 as the I in this modeling. Any questions so far? Now, you can see that in this specific example, my state variables are actually physical component. That does not mean you always going to have that privilege. Okay? So, now, we want to have nth order differential equation. So we are going to have x1 dot, which is q dot, correct? And I dot. Now, q dot, we already know is equal to I. So it's going to be equal to x2. What about this is I dot, why I'm writing like that? I dot. Or let me use prime, that's better. I prime. How we can find it? How we can find I prime? The answer is in the slide, but I want you to like reason about how we find I dot. Any idea what we did to find I dot? The differential of I? We simply replace the definition in our original equation. So we rewrite our original equation, and instead of Q, now we have dot. We have I. So this one is simply the differential of I based on our definition, correct? This one is I itself. Are we good? This one is Q. We don't need to change it because we have the state variable Q. Is that clear? What we are doing? We define our state variable. We want to write two differential equation, first order differential equation that describes the dynamic of these two state variables. The first one is going to be Q dot. Is easy because we define that as I. To find the first order differential equation for the second state variable, we are playing with our original equation. When we have the second d2q over dt2 plus or dq over dt plus 1 over cq equal to vt. Our original equation. We want to play with it, so we have a first order equation for I. To do that, we replace this one with the differential of I. We replace this one with I. And since we already have Q as one of our state variable, we let that to be there. Why we let that Q to be there? What we are doing? Changing the original circuit equation to another equation? What is the purpose of deriving and like finding this equation? Why we did that? We had two state variables, x1 and x2. Eventually, if we want to have a state space model, we need to find x dot equal to ax plus bu, correct? So we need the x dot. What is x dot? X dot is x1 dot and x2 dot. Are we correct? Are we okay? So we need to have two differential equation, one order differential equation that can describe x1 dot and x2 dot based on x1, x2, and input. Because we define x1 as q and x2 as I, we already have one of the first order differential equation. Are we good? Based on the state variable and the input. Is that clear? So we already have this part, what we want for x1. But we need another formula a first order differential equation that describes x2 dot based on our state variable x1 and x2 and the input. Is that clear? So we need to build that equation based on what we have. Now, what we have is that second order original equation. By using the definition that we had, dq over dt is equal to I, we can turn this differential equation into one order differential equation that includes both of our state variable and the input. Is that clear? So we turn this one into a first order differential equation that includes both of our state variable, okay, and the input. Now we have the equations that we want. Now we can drive our a mathematic kind of like analysis and develop the state space model. Any questions so far? Is that clear? Your face doesn't look like that is clear. Ask a question if you want. Yeah.
Can you repeat how you derive di over dt?
Okay. Now, let's just start over. Let's start over completely, okay? We are gonna do that one more time from the beginning. It worth it because we wanted to like be clear instead of just being fast. Now, this is our KVL, correct? We have an integral in our KVL. What we should do? We should
derive, like do a derivation to get rid of the integral.
So we did the derivation, okay? But we discussed that before. We defined another parameter q. Why we replace this q? Do you remember the discussion that we had?
Charge is the derivative of current.
Is the derivative of current. So this integral of the derivative of current will be current. Okay? Is that clear? No, this is I equals to dq over dt, correct? Replace I. This is gonna be dq over dt integral of that over time. So this one become q. This one become the first order dq over dt, correct? And this one become d square q over dt square. Is that clear how we move from I to q? This q does not necessarily represent like a charge or any kind of like concept, okay? Are we good on that? Is that clear? We define the q is a state variable. We define the q, okay? It means something physically, but I don't want to like get into that because we're talking about the state space, okay? That q is actually a physical concept, okay? Now, what we want here is to simply get rid of that integral. So we define the I as dq over dt is the same as getting a differential over that KVL. Is that clear? Let's do the differential. If we do the differential here, what's happening is going to be L I double prime plus R I prime plus 1 over C I, correct? Equal to V prime with the differential, right? Over time. What is the problem here? Why we, instead of getting this differential, we simply defined this I as dq over dt so we can get rid of this integral. We had two options. Is that clear? We had two options. Either change the variable to get rid of that integral, or get the second derivative, second differential over the KVL. Why we did not use the second order, the second differential? Anyone can point that out? We can define every time we can define another variable is mathematical representation. That's your variable, is not a physical variable necessarily. What is the problem with this formula? Do you have problem with this part? No? How about this part? What about this part? Do you have problem understanding that or having that in the system? What about this part? We don't have the differential of input because we don't have the full information of the input over time. Make sense? So we want to avoid that. So we go back, and instead of getting a second derivative, we simply replace I with the derivative of a certain state variable, and that way we get rid of the I, with rid of the integral. Is that clear now? Are we good on that? Now we have our second order differential equation, and we already defined I equal to dq over dt, so we developed that second order. Are we good? Now, forget about these actual values. I wanted to go from the mathematical perspective. You have a second order differential equation. How many state variables should you have? If we have second order, how many state variable we need? Minimum 2, correct? So we have x1 and x2, correct? This is our state variable. It doesn't matter how you define that. I don't want to get into that. Let's say this is equal to C and this is C dot. Okay? Later on, I'm gonna replace that with an actual parameter, okay? Now, we should develop a formula that describes x1 dot and another formula that describes x2 dot. Are we good? Is that clear? So this one is going to be x2, and this one is going to be a linear combination of, like for example, xa1 plus bx2 plus cu. Are we good so far? Linear combination of the state variable and input. Is that clear? I didn't define any variable exactly from the circuit. I just wrote the mathematical formula for the state variables. We need 2 state variables. I just wrote the general formula. Are we good? we have second order, so we have two state variables, x1 and x2. Let's define x1. I use C, so let's as alpha and x2 as alpha dot. Are we good? Is that clear? It's just naming. Now, we need two first order differential equation because we have two state variable. Okay? One is x1 dot, another one is x2 dot. x1 dot is going to be alpha dot, which is x2. Correct? So we have our first differential equation. x2 dot is not in our definition, but we can find it from our original differential equation, whatever it is, or our system. But we already know that it is going to be a linear combination of x1, x2, and input. This is basically the main purpose of using a state space. Is that clear? Now, let's go back to the circuit. Because we defined I as dq over dt, so we can develop our second order differential equation and get rid of that integral, we are going to take advantage of that trick that we did. So we are going to define x1, that alpha, as I, or because I wanted to be precise with this one, x2 as I and x1 as q. I am taking advantage of the trick we did to develop that second order equation. Are we good? Now, that means x1 dot is going to be equal to x2. x1 is q, so q dot is equal to x2, which is I. We already know that, but I wanted to get it from the state space modeling that we have here. Are we good so far? Any question? Now, next one is the x2 dot. Correct? Now, we wanted to have this based on x1, x2, and the input. So we want that x2 dot be a function of q, I, and our input is that v. This is not a v. Is that clear? Okay. Now, look at our original circuit. If we simply use the trick that we did, we can turn this L, second order derivative of Q, into the first order derivative of I. Correct? Is that correct? So, basically, this term is di over dt. Are we good on that? What about this term? This is I. Now, do we need to change this term? No, because our goal is to have both state variables in our function, that f. Are we good? Now, if we replace these with di, dt, and I, we have a new equation that describes the first order differential of I based on q and I and input, which is what we want in the first place. Are we good now? So this A that I have here is what we have times x1. x1 is q, so this is the A I have here. Okay? This is the B I have here, and this is the C I have here. Is that clear so far? Are we good on that? Now, let's put it into a matrix form that we like. That x dot equal to ax plus bu. Okay? Our x dot, we already defined it. If x1 is q and x2 is y, our x1 dot is dq over dt, x2 dot is di over dt. Are we good? Now, what about a? dq over dt is simply equal to x2. So it's going to be 0 times x2. Look at it that way. This is q dot, let's use prime. I prime is equal to a matrix times qi plus another matrix times our input. Are we good? Now, this equation defines q prime or q dot and is equal to x2, which is I. So no q, and we have one I. And we don't have any input, 0. This is our first equation. Second equation says that I prime or di over dt is equal to minus 1 over LC times q. So minus 1 over LC times q plus minus R over L times the second variable, minus 1 over L times the second variable, plus 1 over L times the input. 1 over L times the input. Now we have our state space model for this specific circuit. Any question of how we derive that? Are we good on that? Okay, I don't want to go to the next question because it's gonna be the same, and I wanted to have enough time to explain step by step. So we are gonna continue in the next session. If you have any questions so far, let me know. Otherwise, we are gonna finish our session at this time. Any question? No?
Yeah.
Yes.
I'll figure out that.
Okay. Have a great rest of the day.